Hello, this is DC Circuits, Lesson 1, Lecture 3. So, the third lecture of Lesson 1. And this week we're going to talk a little bit more about Ohm's Law and power equations, and we're going to apply these two equations and mix them up a little bit so you see how they interact. We're going to talk a little bit how power also translates mechanically. Once again, we're going to talk a little bit about how we pay for power in our homes. But first, we're going to do a quick review and look at resistors. So, a quick review over Chapter 2. And so, first thing was we had resistor types. Of course, we had 5-6 different kinds of resistors. And start off here. The first one is our most common type of resistor that you find in electronics that have axial resistors. And an axial resistor just means it's a resistor put around a flat lead. And this is a carbon composition type resistor, or carbon comp. C-A-R-B-O-N, carbon comp. It's the least expensive resistor. Generally has got a greater tolerance. That means it's not quite as accurate. So you're going to either have plus or minus 5 or plus or minus 10% tolerances on these type of resistors. So they will get you in the general area of where you want to be. Then you have film type resistors, and these are two different types. There's a carbon film, C-A-R-B-O-N, carbon film, and metal film. So two different film type resistors, and basically it's a ceramic layers of carbon or metal film layered together. Then they get an epoxy coating, and of course there's axial leads on these guys too. Then you have chip resistors. See, no solder leads. There are solder leads, but they're not wire leads. They're just right on the edge because these solder straight onto a printed circuit board. So there's no holes or anything like that. These are surface mount, and the solder gets soldered on the end here. When you're looking at the values on these, you're either looking at a printed value or you're going to look at 3 color dots, and we'll get into the color code again in just a second. Then you have thermistors, and these items change value as they heat up. So they can have a positive coefficient, that means they get to be more resistance as they get hotter, or a negative coefficient, which means the resistance goes down as they get hotter. You have wire wound resistors. Wire wound resistors are usually used in power applications where you need to have low resistance but high power. And it's wire wound around ceramic film, and once again with an epoxy coating. So lower resistance but higher power. Thus the size of them tells you they're higher power. In this case, that's a potentiometer. It's a variable resistor, but once again it is still wire wound. So where the contact here makes contact with the wire, it will change values depending on where you're making your contact. And then, of course, you have fusible resistors. Now, this one happens to be a 0 ohm resistor. So when you reach it, it has 0 ohms. But when the power gets too big or too much for the size, it's going to open up. So it becomes just like a normal fuse. Otherwise, it's a jumper. So 0 ohm, just you got a black stripe on it. And once again, we're going to look at the stripes in just a moment. So, carbon composition, film type, chip resistors, thermistors, wire wound, and fusible resistors. Different types that we have. All right. Most carbon comp and many metal film have got a color code to tell you its value. Now, this is a 4-band system in this case, and that is the first band gives you the first number of the value, Second band gives you the second value, second number in the value, goodness. And the third band is a decimal multiplier. So like we talked about last week, first number is 2. 2, red, corresponds to the number 2. Second number is 5, because green is the number 5. The third number is your multiplier. It is red, so it is your decimal multiplier, so that's times 10 squared, or you have 2 zeros. So this is 2,500 ohms, or 2.5 k ohms. And then the fourth band is your tolerance, where gold is 5%. But if it was silver, it would have a 10% tolerance. If we're going less than 10 ohms, well, here's the original in the 4-stripe system. Here's another value in the 4-stripe system. And this one is a special value because the third stripe is not a multiplier. A decimal, well, it is a decimal multiplier. But gold and silver in the third spot means you're going to multiply by 0.1. Or if it's silver, you're going to multiply it by 0.01. So you're not going upward in value. You're taking it downward in value. So here, where it was 2,500, because it was 25 times 10 squared, over here, it's 25 times 10 to the minus 1, or 0.1, which is going to equal 2.5 ohms. So you see in the third position, gold is either multiplying by 0.1 or silver is multiplying by 0.01. So we're able to go lower than 10 ohms and still use a color code to give us the value. Now, metal film type resistors, we're going to have more stripes because their tolerances are much tighter. So you got your first number, you got your second number, you got a third number, then you have the multiplier band. Okay, in this case, saying it's orange, so orange is 3, blue again is 5, blue is 6, so 3, 6, green is 5. Black is going to be times 10 to the 0, because black still corresponds to 0. And then the fifth band is your tolerance. And your tolerance can be any of these colors. So in this case it's green, which means I've got a tolerance of 0.5%. Plus or minus 0.5%. So that's a pretty tight tolerance. We can go all the way down to 0.1%. So an extremely tight tolerance. So once again, this is normally what you're going to find in your film type. Not too often in carbon comp are you going to find these type of tolerances. Alright, now when we talk about the tolerance, they've got these resistors facing the wrong direction, because normally we're going to read from left to right, but we can still read from right to left. So 102, so this is 1,000 ohms, plus or minus 5%. So if you look at 1 kilo ohm, 1,000 ohms, plus or minus 5%, this is the range of actual value that resistor can be. This one is 390 ohms, orange, white, 1. So 3, 9 times 10 to the 1. So 1, 0. So 390 ohms plus or minus 5%. So once again, we have this kind of range. You never have to tell us what the range is unless asked specifically. If you're asked the tolerance, tolerance is plus or minus 5%. Then anybody asking the tolerance should have brains enough to go out and figure it out themselves. Okay, our variable resistors, such as rheostats or potentiometers. Rheostats are generally in line with the circuit. They're going to control the voltage going into the circuit, which means they're also going to control the current. They're going to control the current flow in the circuit. So they're going to actually change the resistance of the overall circuit. Thereby, if you change the resistance, you also change the current flow. And these are a couple of ways of it being shown right here. Oh, somehow I lost the potentiometer slide. Well, potentiometer is a little bit different. I'll just throw a new page in here. A potentiometer, a rheostat's got 2 leads, and is in line with the whole circuit, whereas a potentiometer has got 3 leads. And will generally control the voltage to another load out here. So by tapping off the voltage source, we control a different. There's voltage A. Feeding the load will be voltage B, depending on the tap of your potentiometer. In the most classic of anybody in my age group, that's going to be the line going out to the speaker so you can control the volume. All right, after resistors came chapter 3, which is Ohm's law. And of course, we discussed basic Ohm's law. We talked about the proportionality between voltage and current and resistance. We talked a little bit about electric power. And we haven't really gotten too much into this portion right there. So this is going to be our main objective for today. But for a real quick review on Ohm's law and the linear proportion between voltage and current and resistance, we'll move along. So Ohm's law, in its purest form, voltage equals current times resistance. And if you've forgotten the symbols, the formula symbols for current, resistance, and voltage, there you go. Of course, the unit of measurement is the amp, the volt, and the ohm. So the purest form, voltage equals current times resistance. But using Ohm's law to derive a formula for current, we see that current equals voltage over resistance. And deriving the formula for resistance, resistance equals voltage over current. Now this should be something that becomes second nature to you, because Ohm's law is the basis of all the electronics going forward. Okay, now just applying the basics of Ohm's law. if you know what your voltage source is and you know what your resistance is, your current flow through this circuit will have to be voltage over resistance, or 20 volts over 4 ohms, 5 amps. In the pure form, if you know what your current flow is or what current flow you're going to require, and you know what your load is or your resistance, well, current times resistance, 1 amp, times 12 ohms, your voltage source will have to be able to handle 12 volts. If you know what your voltage source is, and you know what the current requirement is, you can figure out what the load resistance is going to have to be by simply voltage over current, 6 volts over 3 amps. Your load has to be 2 ohms. It's as simple as that. Now, I've mentioned several times, current and voltage are linear for a given resistance. Let's go back and look at the equation again. Voltage equals current times resistance. So for a given resistance, a constant linear resistance, that is a resistance that's not going to change with voltage or heat or anything like that. So we're just going to say resistance equals 1. We'll even call that 1 ohm. So voltage equals current times 1 ohm. Voltage equals current, which means if voltage goes up, current has to go up. It has to go up the same. Your resistance isn't changing. Now your resistance can scale it, okay? If I make that 2 ohms, as your voltage goes up, your current will go up in greater proportion because, of course, you're multiplying it by 2. So the resistance will act as a scaling factor for the current, but voltage and current are directly proportional. However, that said, for a given voltage, and we'll call voltage equal to, whoops, I'm pressing a button I shouldn't be pressing there. So let me erase that real quick. Okay, said voltage equal to 1, so it's constant. It cannot change. So if current goes up, in order to maintain that constant voltage, your resistance has got to be going down. If resistance goes up, current then will decrease. So current and resistance are inversely proportional. Voltage and current are directly proportional. Resistance and current are inversely proportional. And this is just a graphic that demonstrates that for a fixed resistance, as your voltage goes up, your current will also go up. Now, of course, it's scaled. So if you increase 2 volts because your resistance is 2 ohms, your current is only going up 1 volt. Go up 4 volts, your current's going to go up another amp, etc. You're always going to be scaled by the 2 ohms. But still, you're going up on a straight curve. Now, as I said, when voltage is constant, current and resistance are inversely proportional. So they have an inverse relationship. Back to the linear proportionality of voltage and current. You can see you increase the resistance, all you're doing is changing the slope of the current voltage line. If you decrease the resistance, you just make that current slope steeper. Not all resistances are linear. In the case of a light bulb here, when that tungsten filament heats up, as it heats up, its resistance increases. As its resistance increases, you see the current slope getting shallower. Because, once again, as resistance goes up, current has to go down. In this case, a thermistor with a negative coefficient, which means it's going to get smaller. As it heats up and the resistance gets smaller, you can see that current slope increasing, getting steeper. So now we have Ohm's law. You see that we can, from knowing two items, the resistance or the current, we can then and the current or resistance and the voltage, or the current and the voltage. From any two items, we can always calculate the third. We've got three different equations we can use based on Ohm's law to do it. Now we get into a third part of electronics, and that is power. Of course, as current flows, the flowing electrons, which are actually particles, create friction. The faster they move, the more friction, you generate heat. In electronics, that heat is an example of power consumption. So that is power. And power is calculated as voltage times current, or power equals V times I. Now, power can also be, by the way, power is measured in watts. And the symbol is, or the units are W, or large W, I should say. Now, watts is a measurement for power output for pretty much anything dealing with power. Mechanically, we can relate 1 horsepower is equal to 746 watts. In cycling, they calculate how many watts you're burning, or how many watts of power you're putting out in your legs. In motors, you've all seen 1 horsepower motors, half horsepower motors. Even using electric motors, an electric motor has a horsepower rating. So power can be translated mechanically also. Now, that goes to the work and energy aspect of it. So in electronics, voltage times current. Overall, power is the time rate of doing work. So work, as in joules, small w, power is the time rate, or work energy output per second. So power equals work over time. Or work is power output times the amount of time you're putting out that power. which will come in handy in a minute. So how do we get to this? How do we get to this from this? Well, you'll recall from chapter 1 that a volt is the energy, 1 joule, so the amount of work energy required to move a coulomb of charge. And the amp is the time rate of flow of charge, 1 coulomb of charge past a given point in 1 second. So power equaling voltage times current, the charge cancels and you end up with work over time. Why is this important? Well, we can measure the number of joules, the amount of work energy that's expended at any given time by something that's using up work energy. From that, we can derive several aspects of the device that is using that energy. For example, I have an appliance. It's got a motor in it. That motor is a quarter horsepower motor. And it uses 23.3 megajoules of energy in some period, in this case 18 hours. Now we're going to assume that this is an American appliance, so it's working off approximately 120 volts household voltage. And that household is paying the minimum California tier of 15 cents per kilowatt hour. From this information we have here, we can determine the rated power consumption of the appliance. Now, you've seen power consumption ratings on most of your appliances. If you look, a light bulb is 100 watts. That means it's going to consume 100 watts of power in 1 second. Okay, that is the power rating. That has nothing to do with power consumption in the fashion in which we pay for it. That is the power rating of the item. So from this information, we can determine the rated power consumption for the appliance. We can determine the efficiency of the appliance. And that goes back to the fact that the output of that appliance is supposed to be a quarter horsepower. Now, how much energy does it take to actually generate that 1/4 horsepower? We'll be able to calculate that. Of course, since we can determine the rated power consumption of the item, and we know the voltage source for the item, we can find out what the current rating for the item is. Since we can determine the current rating, we can also determine what the average load or what the resistance of that appliance is. And of course, in the end, we'll be able to figure out how to calculate the cost of running that item. All from knowing the equations that go into power. So let's start with, what is the rated power consumption of the appliance? Well, to do that, we've got to figure out how much power this thing is going to use every second. So, I know that power is equal to work over time. Notice that's a small w. work over time, and time is rated in seconds. I know that 1 hour is 3,600 seconds. 60 seconds per minute and 60 minutes in each hour. So 3,600 seconds is 1 hour. So now I just have to figure out how much power is consumed every second. Well, the power is going to equal 23.3 megajoules, so 23.3 million joules, over the number of seconds it used up this 23.3 megajoules of work energy. So 18 times 3,600. So if you do 23.3 megajoules over 18 times 3,600, you're going to come up with a number like 359.567900123, etc., 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 or approximately 359.57 watts. P is approximately equal to that. So this is the power rating. When you look on the label, it's going to say 120 volts, so many amps, probably about 360 watts. Now, what was the second item we wanted to figure out? Well, first we determine the rated power consumption. Now, the efficiency of the appliance. Well, the efficiency of the appliance is how much power do I have to put in to get that quarter horsepower out? Well, I know that 1 horsepower equals 746 watts. So quarter horsepower equals 186.5 watts. I know that this appliance is using 359.57 watts to produce this. So it's basically just a formula of power out over power in. So this quarter horsepower motor is actually running at 52% efficiency. So there's how we get to an efficiency rating. Now the current required to run this guy, well, I know power equals voltage times current, or current is equal power over voltage. And my power equals 359.57 watts. My voltage equals 120 volts. So my current equals power over voltage, or 2.996 amps, approximately 3 amps is the current rating for this appliance. The average load, well, voltage equals current times resistance, or my resistance equals voltage over current. So 120 volts over 3 amps. My average load resistance is 40 ohms. So you see how we're breaking this down just because I knew how much work energy was used over a specific period of time. And then, of course, there was also knowing the household voltage that was running it. Now, power usage, the way we pay for power usage. Our power usage is determined off of kilowatt hours, which means the power rating of the item expressed in kilowatt hours times the number of hours that it's used. So in this case, I've got a 240 volt item with a current flow of 20 amps. Well, the power rating for this item is voltage times current, so 240 volts times 20 amps, or 4,800 watts, converting that to kilowatts, 4.8 kilowatts. Now, how many hours is it running? Well, here it says it's running half a day. So the power rating times the number of hours that it's rated to run. So 4.8 kilowatts times 12 hours equals 57.6 kilowatt hours. And then you just multiply by the rate that you're paying. So in this case, it's 8 cents per kilowatt hour. I'd love to live there. So 57.6 kilowatt hours times 8 cents. This air conditioner runs about $464.61 a day to run. Once again, I would love to live in this place. Well, let's apply that to our power. Our power consumption, or our rated power, our power rating, is 359.57 watts. Converting that to kilowatts, or dividing it by 1,000, I'm at 0.35957 kilowatts. Multiplying by the number of hours we operated the appliance, which was 18, I used 6.47 kilowatt hours running that appliance. At our rate of 15 cents per kilowatt hour, 6.47 kilowatt hours times 15 cents equals 97.1 cents, so about 97 cents a day. Approximately 97 cents a day to run that item. So that's how we pay for the electricity. So you can see there's a difference between the power rating and power consumption. Remember that when it's a circuit's power rating is different from the circuit's power consumption, the way we pay for power. All right, when current flows, of course, current going through a resistance, heat is produced from the friction of moving free electrons and atoms obstructing their path. Heat is evidence that power is used in producing current. The amount of heat that we're producing, once again, since the evidence of power, that heat and power kind of go hand in hand. So we have to have a device that is going to handle the amount of heat or the amount of power that's going through. Now, how do we figure that out? How is the resistor that we choose, how are we going to figure out how much power we're going to be using there? Well, we're going to use Ohm's law and the power formula, and we're going to intermix them. We're going to use substitution from Ohm's law into the power formula to come up with the numbers that we need. So we can use combinations of Ohm's law and the power formula through substitution. We got voltage equals current times resistance, and power equals voltage times current. So through substitution, we're going to be able to introduce resistance into our power formula. So since voltage equals current times resistance, we can substitute this value for the V in the power equals voltage times current, or power equals current times voltage, or power equals current squared times R. Using the second derivative of Ohm's law, if V equals current times resistance, then current is going to equal voltage. That shouldn't be over I, that should equal R. Current is going to equal voltage over resistance. So how about we substitute that for current there? So power now equals voltage times voltage over resistance, or power equals V squared R. So this allows us to introduce resistance as an element of power, and it allows more calculations when one or more value is unknown. And that's just the start. Don't forget, Ohm's law mixes in here. Okay. Expressing power in terms of voltage and current, of course, we have power equals voltage times current. Current equals power over voltage, or voltage equals power over current. Substituting for voltage, we now recall that power equals current squared times resistance, or resistance equals power over current squared, or current equals to the square root of power over resistance. Substituting for current, of course, power equals V squared over R. R equals V squared over P. Or voltage equals the square root of power times resistance. This guy becomes very handy all of a sudden, because I know for most circuits I know what voltage I'm going to be operating off of. I know what power, or pardon me, yeah, I know what, wait, that's maximum rating. Sorry. I know what resistance I need to be working off of, so I'm going to want to be able to figure out power. So this is the one I wanted to go for to start with. Okay, we're going to keep on going here real quick. All right, we'll get to those calculations in a minute. Just applying the power formulas. The standard, I've got 20 volts, I got 5 amps. I calculate power off of that at 100 watts. Substituting, I know my current, I know my resistance. Who cares what voltage is at this point? If I've got 5 amps of current times my resistance, 25 times 4 equals 100 watts. That seems to be the same. I'm not too worried about current because I've got my voltage and I know my resistance. Since I know my voltage and resistance, power equals V squared. 20 volts squared, 400. Divided by my resistance, 4. Power required is still 100 watts. So all of a sudden I don't necessarily need to know voltage or current if I know what my resistance is. I can work off any of the other two. Now here's where all those variations start coming in handy. When we're choosing a resistor, when we did the resistor chapter last week, I showed you a picture of different wattage values, different power values for resistors, and you saw different sizes of the same value. So what size do you choose? Well, you got to determine the resistor size for the basic circuit. So what's the required resistance value? You can calculate the power dissipated that's going to be dissipated by the resistor using any of the power formulas. And then we select a wattage size that's going to give us a buffer, and we normally double that. However, it is possible to get a wattage size and a resistor value that still won't work within voltage limits. So you have to be able to work within the maximum working voltage rating. So for carbon film resistors, each size has got a maximum working voltage. So if I come up with a value for a resistor that says it's only going to use an 1/8 watt, but I'm working at 150 volts, that's not going to be the one I want to choose. I will want to go up to the next size and give myself some buffer room for the working voltage. Now if my calculation says I need a 1/4 watt, and I'm also approaching the voltage limit, well, let's go up again. If I need a 1/4 watt, let's go up to a 1/2 watt and make sure I've got enough power buffer and voltage range to work off the circuit that I'm building. Okay, but in general, we can work in this range here. Your maximum working voltage for a circuit is going to be the power rating for the resistor times the resistance, and of course the square root. So the maximum working voltage may be exceeded before the power rating is exceeded. And if you do that, you're going to cause internal arcing of the resistor, so you're going to cause the resistor to break down and become a hunk of wire instead of a resistor. Let's see here. So be aware of all those things. Here we go. Electrical shock. Electrical shock is a hazard, of course, for any technician. And there are precautions you have to take. Of course, removing rings, watches, jewelry, anything else that is conductive when you're working on a live circuit is a must. You should also work, if you're going to reach in, make sure it's a cold system before you start hooking up your meter and all that. Once your meter's hooked up, you can turn the system back on. But if you got to work on a hot system, use only one hand. Put your other hand behind you, put it over your head, stick it in your belt. Just keep it away from the circuit, because you do not want current flowing from hand to hand through your heart. It doesn't take much current at all to cause your heart to stop working. So make sure you only are working one hand. Wear your rubber-soled shoes. Wear your rubber glove. Keep yourself insulated from earth ground. Once again, current is going to flow from whatever part of the body you're touching that hot circuit through to the ground. So if you're leaning against something that's grounded and you've got your other hand in a hot circuit, you're giving yourself a hand-to-hand conduction. If you're working barefoot on a concrete floor, you grab that hot lead, you're giving a path through your heart to the ground. Not to mention the fact that even if you're not going through your heart, current causes heat. Heat will kill muscle. It's just a bad thing. So where you go, there you go, hand to hand, bad stuff going through your heart. So be aware of electrical shock possibility when you're working in electronics. Now, once again, our section on troubleshooting, because we always have a good time in troubleshooting. All right, normal circuit, complete circuit, current flow, you got 10 volts, resistance of 5 ohms, which means you're going to produce 2 amps of current flow. That's a good circuit. However, if you get an open, whether it's an open in the resistor or an open somewhere in the path, means infinite resistance with an open path, there is no current flow. So if you stick a meter out here, you're still going to read the value of the power source, but if you stick a current meter in line, you're going to find that you have no current flow, 0 amps. Then you have the short circuit. Once again, you got a beautiful circuit here working like a champ. Over here, you got 10 volts, and somehow you got a short, a hunk of wire across your resistor. What you got is a hot piece of wire forming here because you've got infinite current flowing around that resistance. That resistor may as well not even be there. Current will take the easiest path every time. So you got excessive current, which means you have high heat and a very hot piece of wire there until it either opens or your trace opens. Something bad is going to happen. And in all honesty, that is the end of chapter 3. So, if you take nothing else out of this chapter, you want to remember your 3 forms of Ohm's law. You want to remember your power formula and how to substitute Ohm's law. Oops. How to substitute Ohm's law into the power formula to create your 9 different forms of power. So 3 forms of Ohm's law will give you 9 combinations for calculating power, calculating current, calculating voltage, or calculating resistance. You just need 2 out of the 4 to determine the other 2. Of course, remembering how to calculate from sorry, from your power formula here being able to calculate power consumption, efficiency, current, load, of course, being able to calculate how much you're paying for electricity, well, that would be a good thing for you to remember too. All right, but that's about all I have for today. Once again, if you have any questions, feel free to contact me. You know how to do it. You can do it through Blackboard. You can do it through email. Just be sure you contact me if you start running into problems. I will be more than happy to answer your questions. Just don't let yourself get stuck. Other than that, once again, I'm available for live answers on Wednesday evening from 5 to 7 Pacific time, or 7 to 9 Central Standard Time, which is the school's time. And that's about it. So I'm going to wrap this up. You guys have a good week, and I will talk to you later. Bye.